All right, let's get ready for a deep dive today, folks, into inductive AC circuits. You know, you said there's a ton of material on AC circuits.
Yeah, it looks like textbooks, chapters, notes, even some knowledge-based assignments.
Yeah, a real mix.
But it seems like you're especially interested in inductors.
You hit the nail on the head. So whether you're studying for an exam or working on some kind of project or just, curious about how the world works.
We're here to make it all make sense.
Yeah, exactly.
And to help you really remember this stuff.
Make it a little bit fun.
Yeah, for sure.
Looks like we've got Chapter 16, Inductive AC Circuits from a textbook.
Oh, perfect.
All right, so how about we start with a really quick recap of AC and DC? Just the basics,
Sounds good.
I'm sure you're already familiar with this stuff, but
Always good to refresh.
never hurts to refresh. Direct current is DC.
Right.
And that's like a river, just flowing steadily in one direction.
Yeah, makes sense.
And the positive and negative terminal,
They stay the same.
it's constant, yeah,
Yeah.
like a battery.
Exactly. A battery is a perfect example of a DC source.
Yeah. No, AC, alternating current.
That's a whole different story.
It's a little more chaotic,
A little bit, yeah.
more like waves crashing on the shore,
Yeah, back and forth.
back and forth.
Yeah.
The current flow reverses direction.
At a regular rate.
Yeah, it's got that rhythm.
Yeah, and that rhythm is the frequency,
Oh, right.
the number of cycles per second.
Okay.
And that's where that sine wave comes in.
Oh, yeah, the sine wave.
You know that up and down curve?
Yeah,
That shows how the voltage and the
and
current,
they alternate over time.
they do.
Okay, I can picture that.
Good.
So where do inductors fit into all of this? We'd see them all over these materials you sent.
Yeah, inductors.
What are they all about?
Well, an inductor is basically a coil of wire,
Okay.
but it acts like almost like a tiny little inertia machine. An inertia machine for electricity.
Okay.
It wants the current to stay steady.
Really?
Yeah. It resists any changes.
So it doesn't like AC very much then?
No, not really. No, it much prefers that steady DC.
Okay.
Almost like a stubborn donkey.
A stubborn donkey.
Yeah, you try and get it to change direction.
Then it resists.
It's going to push back. Exactly.
That's a great analogy.
And that pushback, that's what we call inductive reactance.
Inductive reactance.
Yeah, and we represent that with XL.
XL. Okay.
And it's basically the opposition the inductor offers to that AC current.
Okay, so the faster the AC switches direction, meaning higher frequency?
The more the inductor resists.
So it's not like a fixed resistance then?
Yeah.
Like a resistor?
Not at all.
Okay.
It changes
Mm-hmm.
depending on the frequency.
So it's dynamic.
It is dynamic, exactly.
Okay.
Think about shaking a heavy weight back and forth.
Okay, I can picture that.
The faster you try to move it,
The harder it is.
the more resistance you feel.
Right.
And that's kind of similar to what's happening with an inductor in an AC circuit.
Okay, that makes sense.
Yeah.
So if I wanted to block out those really high frequency signals,
You want a bigger inductor.
bigger inductor is better.
Exactly. Now, what about phase shift?
Phase shift.
We saw that in some of these sources.
Yeah, that's another really interesting phenomenon.
Yeah.
So in a purely resistive DC circuit,
Okay.
the voltage and the current
They're totally in sync.
perfectly in sync.
Okay.
But with AC,
Things get out of sync.
they do. They're out of step like dancers,
Mhm.
with slightly different rhythms.
So they're not peaking at the same time.
Exactly.
Oh, what?
In an inductive circuit,
Okay.
the voltage, it leads the current,
Okay.
like two runners on a track.
Yeah.
Voltage starts a little bit earlier.
Okay.
So it's always a step ahead
Of the current.
of the current, exactly. And that out of sync
Makes
run,
the phase shift.
that's the phase shift.
Okay. I think I'm starting to visualize it.
Good.
But why is this phase shift so important
Well, it turns out this out of sync dance,
between the voltage and the current?
yeah, it's super important because it affects how the
Power.
power is delivered and used in the circuit.
Oh, wow.
But that's a whole other deep dive.
Oh, other deep dive, yeah.
Yeah, for another time.
Another time.
But for now, just remember that inductors in AC circuits,
Okay.
they make this whole relationship way more dynamic
Then in simple DC circuits.
than in simple DC circuits, exactly.
My brain is doing like backflips trying to imagine all this.
I bet.
But I think I'm getting it.
That's good. That's good.
Now, what about those notes about AC measurements?
Oh, yeah, those are going to be really helpful.
Those are pretty dense.
Yeah, they are a bit.
I don't know if I understood all
Well, we can definitely break them down
that. Okay,
and see how these inductors
yeah.
really behave in action.
All right, let's do it. Okay, so we're talking oscilloscopes and all those other gadgets.
Exactly. All the tools of the trade.
I gotta admit that part of my notes felt a little
overwhelming.
It's a lot to take in.
Yeah.
But remember, each tool has a specific purpose.
Okay.
It's like they're extensions of our senses, you know?
Extensions of our senses?
Yeah, helping us see this invisible world of electricity.
I like that. So where do we start? Which tool is the best for like really seeing what's going on with an inductor?
In an AC circuit.
Yeah.
Well, for that, the oscilloscope is our king.
The oscilloscope.
Yeah, it lets us see the actual waveforms, you know,
A waveform.
of the voltage and the current.
So we can see that phase shift
Exactly. You can see the voltage wave leading the current wave.
right on the screen.
Right there on the screen. And we can measure the time difference between those peaks
Oh, wow.
to quantify the phase shift.
Okay.
Plus, we can see how those wave shapes change.
As we adjust the frequency.
Exactly.
That's really cool.
It is. It's pretty amazing.
It's like having X-ray vision for circuits.
It is, kind of.
But my notes also mentioned D'Arsonval meters and iron vein meters.
Oh, yeah.
What are those all about?
So those are types of analog meters.
Analog.
Yeah, and they're a bit simpler, less versatile than the oscilloscope. The D'Arsonval movement that's designed for DC measurements.
Oh, so DC only.
Pretty much, yeah. So we'd need to add some extra circuitry
Okay.
to convert the AC to DC
To use them.
before we can use them right.
Gotcha.
Iron vein meters, those can measure AC directly.
Directly. Okay.
But they're better for lower frequencies.
Lower frequencies. Okay.
Yeah.
So they've got their limitations.
They do.
What about those clamp-on ammeters?
Ah, the clamp-on ammeter.
Those were always fun to use in the lab.
Those are great.
Yeah.
They're a favorite for measuring AC current
Okay.
without having to interrupt the circuit.
Oh, that's really convenient.
It is super convenient.
Yeah.
And remember how we talked about the inductor creating a magnetic field?
Uh-huh.
Well, the clamp-on uses that principle.
Really?
Yeah, to sense the current flowing through the wire.
So it's like magic, but it's not
It's not magic.
just science?
It's clever engineering
Okay.
based on electromagnetism.
Got it. So we've got tools to visualize those waveforms. We've got tools to measure the current.
Mm-hmm.
And my notes even mentioned a Bode plotter.
Ah, the Bode plotter.
What's that all about?
So the Bode plotter is less about those individual waveforms
Okay.
and more about understanding the circuit's overall frequency response.
The frequency response.
It generates graphs.
Okay, so not squiggly lines, but graphs.
Graphs this time.
Okay, what kind of information do those graphs tell us?
Well, they show us how the circuit amplifies or attenuates signals
At different frequencies.
at different frequencies, right? And how that phase shift changes
With frequency.
with frequency, exactly. This is super valuable for analyzing filter circuits.
Filter circuits.
Yeah, you know, the circuit's designed to let some frequencies pass through
And block others.
and block others, right?
Okay, that's starting to sound a little more advanced.
It is a bit, but remember, we're building up a multidimensional understanding here.
Multidimensional.
Yeah, we've got tools to see those individual AC signals,
Okay.
tools to analyze their frequency, and now tools to understand how the whole circuit behaves.
Across a whole spectrum of frequencies.
Across a whole range.
Wow, that's a lot of tools.
It is.
But let's not forget about the star of the show,
The inductor.
the inductor. How do all these tools help us understand?
Those inductive AC circuits.
Yeah, from Chapter 16.
In Chapter 16. Good question.
All right, so we've got all these cool tools to analyze these circuits,
They do.
but I'm ready to get back to those inductive AC circuits,
From Chapter 16.
from Chapter 16, yeah. What happens when we bring inductors and resistors together?
Ah, that's where the fun really begins.
The fun begins.
Yeah, in a purely resistive AC circuit.
Okay.
A lot of the rules from DC circuits still apply.
Really?
Yeah, things like Ohm's law,
Ohm's law.
Watt's law,
Okay.
Kirchhoff's laws.
They all still work,
They all still work.
even though the current's going back and forth.
Exactly.
Wow.
There is one important difference, though.
What's that?
In AC circuits, we often use what's called the effective voltage.
Effective voltage.
RMS voltage.
RMS voltage.
Okay.
And that's basically the AC equivalent of a DC voltage.
Okay.
That would produce the same amount of heat in a resistor,
Okay.
and that's usually the value you see on a multimeter.
All right, that makes sense. So in a purely resistive AC circuit, it's kind of like a DC circuit.
Yeah, you can think of it that way.
But we're dealing with these RMS values.
Exactly.
Okay, but what happens when we add that inductor?
That's when that phase shift we were talking about.
Oh, right, the phase shift.
Yeah, that really comes into play.
Okay.
Remember, the voltage leads the current in an inductive circuit.
Uh-huh.
That phase difference.
Yeah.
It affects how the resistor and the inductor interact.
So it's not as easy as just adding up the resistance and the inductive reactance.
Nope, not that simple.
Okay.
We have to use something called phasor addition.
Phasor addition.
Yeah, it's a little more complicated.
It sounds kind of intimidating.
It might sound a bit intimidating.
Yeah.
But it's basically a way to visualize
the relationship between voltage and current in AC circuits.
Taking into account the phase.
Taking into account both magnitude and phase.
Okay.
Chapter 16 actually has some diagrams that explain it pretty well.
Oh, yeah, I see those now.
Yeah, those arrow diagrams.
Okay, so those phasors help us figure out the combined effect.
Of the resistor and the inductor.
Of the resistor and the inductor.
Right.
Okay. What else does Chapter 16 tell us about these circuits?
Well, it talks about impedance.
Impedance.
Which is the total opposition to current flow in an AC circuit.
Okay.
Taking into account both resistance and reactance.
So it's the total picture.
Total picture.
Yeah. Hey.
And it also introduces the concept of power factor.
Power factor.
Which is basically a matter of how effectively the circuit converts electrical power into useful work.
So not all the power from the source is actually doing something useful.
That's right.
Oh, wow.
The inductor stores and releases energy in its magnetic field.
Yeah.
So some of that power is kind of just sloshing around.
Sloshing around.
Yeah, not really doing any real work.
So the power factor tells us how much is actually getting used.
That's a good way to put it.
Okay. Anything else?
Yeah, it also gets into analyzing series and parallel inductive AC circuits.
Okay.
And uses those phasor diagrams
Right.
and some calculations
Okay.
to figure out the voltage, current, and impedance.
Across different parts of the circuit.
Yeah.
So we're talking serious circuit analysis here.
We are getting into the nitty-gritty.
I'm starting to see how all this ties together, though. You know,
Yeah.
We've gone from the basic concepts of AC and inductors
Yeah, step by step.
to how they interact in a circuit, and now we're even analyzing complex circuits.
And remember all those tools we talked about?
Oh, yeah, the oscilloscope and everything?
Those are essential for actually visualizing and measuring all this stuff in real life.
Right. We can see those phase shifts, measure the impedance,
Exactly.
and analyze those frequency responses.
With all those gadgets.
With all those gadgets. Wow, this has been quite a journey
It has.
through the world of inductive AC circuits.
Yeah, it's amazing how these fundamental principles shape the technology all around us.
It really is. And for our listener out there, remember, this is just the beginning. Keep exploring those resources.
Keep asking those questions.
Keep that curiosity burning.
And who knows, maybe one day you'll be designing the next groundbreaking electronic device.
Powered by these very same principles.
Exactly.
Until next time, folks, keep on diving deep.